So we talked about numerical conditioning, right? Conditioning was a property of the problem. And then we talked about numerical stability, which is a property of the algorithm used to solve the problem. And essentially what we looked at last time was the numerical stability of the dot product, which allowed us to show that the computed dot product was equal to the dot product of a slightly changed input, which was the definition of numerical stability. And then we used very quickly the dot product to implement the matrix vector multiply. And what we then saw was that the matrix vector multiply, the computed matrix vector multiply, was equal to a slightly changed matrix vector multiply, where the matrix A was slightly changed. Yes?
Can you put screen down?
We could put, well, we actually don't need it yet, so let me just sort of blank it out for now. But yeah, it's distracting at the very least. We can continue with that, but the fact is that it would be good to have some slightly more complicated operations to look at in order to further illustrate how the stability of algorithms is established. So what I'm going to do now is I'm going to rush ahead into the next topic, which is LU factorization. And then we will revisit numerical stability by looking at the numerical stability of LU factorization and LU factorization with partial pivoting. And one of the things that this will allow us to do is to get a little away from the nitty-gritty math of linear algebra and instead look at linear algebra hand in hand with algorithms again, which we looked at a little bit when we looked at household and QR factorization, but we certainly have sort of seen only math ever since, right? Every once in a while we need to cleanse our brain and do something else. So the LU factorization is simply Gaussian elimination. Okay? And what was Gaussian elimination? Well, let me just sort of sketch it out. Well, maybe we should sketch it out with an example, but in order to do an example, I probably should quickly generate an actual example that will work out nicely, so let me do that. And for this, I guess we can put the projector down.
What do you do? Start with nice numbers and work backwards?
Yeah, that's how I'm going to do it. Okay, here we go. What did I do? Well, I'm going to try to convince you that LU factorization is simply Gaussian elimination. And I just took advantage of the fact that LU factorization is just Gaussian elimination by generating a problem on which we can do Gaussian elimination by first creating an L and U factor, multiplying them together, etc. And I guess we need the solution as well, so we'll and then we'll do A is equal to L times U, and we'll do A times X. And now what we have is, recall that if you have 2 times chi0 plus chi1 is equal to 0, and then, let's just write it down, minus 3, 2, minus 4, minus 3, 1, 3, and 0, minus 3, minus 5. Okay. Here we have a system of linear equations. And recall that to solve this, typically what you did was you converted this into an appended system, so we only had to work with the matrix of numbers. Something like this. Is coming back to you? And then you said, oh, I'll take a multiple of the first row and subtract it off the second row. And what is the multiple that we need to do? We need to do 2 times the first row actually and add it to the second row, right? So we leave the first row alone. And then we introduce a 0 here. And if we do 2 times this and add it to that, we get -2. 2 times that added to that, we get 1. 2 times that added to that is -3. And then we may want to do 1 times the first row and subtract it off the second row, and you get a 0 there. This subtracted off of that gives a -4. This subtracted off of that gives a 3 and a -5. And then you go 1 step further, and you leave the first 2 rows alone. And then the final row, you take 2 times that subtracted off of that, you get a 0. 2 times that subtracted off of that gives a 1. 2 times that subtracted off of that gets a 1.
Negative 11. Oh no.
1, right? 1. And then you end up with an upper triangular system that's much easier to solve.
It's higher than 2. You're not expected to do it, right?
Well, so I always joke that if you were taking a regular linear algebra class, then you would be asked to do a 3 by 3. And if you were taking an honors version, you were asked to do a 4 by 4. Right? As if one learns more from that. And then hopefully, you know, you sort of recognize that there is this multiplier that is just this divided by that was used to multiply the first row and subtract off the second row. And then you get this divided by that was the multiplier here, and the multiplier here was 2. So 2 times this row and subtracted it off that row. And hopefully, magically, you were shown that if you then take all of these multipliers and put them below the diagonal of the identity, and you took this particular upper triangular matrix, magically, if you multiply all of this out, you get the original matrix back. Okay, you can check that. In which case, this was known as the L factor and this the U factor. So just out of curiosity, how many of you saw this in an undergraduate course? Okay. Not everybody, but okay. So if you haven't seen this, I very carefully walked through all of this, I think in weeks 6 and 7 of this massive online course that we created. And you know, I very systematically walk you through all of the steps that allow you to recognize that doing Gaussian elimination is really exactly the same thing as computing the matrix L and the matrix U, such that if you multiply them together, you get the original matrix back. And I then also link what you do to the right-hand side to solving a lower triangular system of equations, and the back substitution that you need to do to actually come up with the solution to the linear system to solve it with an upper triangular matrix. So I strongly suggest that this weekend you actually go through all of that, if everything that I say today isn't immediately obvious to you. Okay? I spent a lot of time on those weeks, and therefore I might as well make you suffer through them. Okay? Now, what I'm going to do in this lecture is show you that if you've mastered the fine art of slicing and dicing, of partitioning matrices, then the LU factorization algorithm just drops right in your lap. Okay? It's just a matter of pushing symbols and everything falls in place. And as I do so, what I'll try to do is relate exactly the Gaussian elimination, with which hopefully you're familiar, to what is happening with LU factorization, so that at the end you go, everything is crystal clear. Okay? And then we'll talk a little bit about how to then add pivoting to it, because all hell can break loose if you're not careful. And then we end up with the practical algorithm that's typically used in practice. And then we'll talk a little bit about how to then solve linear systems with the L and U factors. And then that will set us up to next time talk about a slightly different variant of LU factorization. So the same result, but a different algorithm to attain the same result. And the reason why we'll talk about that particular algorithm is that its numerical properties are a little bit easier to analyze. And therefore, it's easier to do a stability analysis of that result than it is of the classical algorithm that we're going to talk about right now. Not that the results are different, it's just that we might as well analyze something simpler. I like simple. Okay, so that's the plan. So let's see. So the conjecture is that given matrix A, we can compute a factor L and a factor U such that if you, now notice that L is a lower triangular matrix but has ones on the diagonal. We call that a unit lower triangular matrix. And U is upper triangular. Multiply them together, you get A back. Okay, why is this useful? This is useful because if you're trying to solve AX equals B, then you can substitute in LU for A. You can then conveniently place some parentheses, and you can recognize that if we first take L and B and solve for intermediate value Z, that's just solving a lower triangular matrix, which hopefully at some point in your life you notice is simpler. And you then solve Ux is equal to Z, which is solving with an upper triangular matrix. Then notice you get the solution to AX equals B. People do this instead of computing A inverse. And again, in the massive open online course in week 8, we try to point out that it's a really bad idea to compute A inverse. And it turns out that it's actually numerically less stable to compute A inverse and then multiply with that matrix as well, which is probably something we don't really get into, but it's something you should be aware of. So computing the inverse of a matrix is rarely a good idea, which is why I have several papers on how to compute the inverse of a matrix. There are occasions where it's a useful thing to have. All right, we sort of understand where we're headed with all of this. I'm going to have to be careful that I keep things up. Yeah, I think I can manage. Okay. When in doubt, partition matrices. So, by the way, it is not the case that the LU factorization always exists. It's certainly the case that if A is not singular, then you run afoul. But even if A is not singular, you can run afoul. For example, if you do Gaussian elimination on this matrix, clearly it has linearly independent columns, so it has an inverse. But Gaussian elimination would start by dividing by 0. And there's no way of taking a multiple of the first row, subtract it off the second row, and introduce a 0 here. And therefore we've got a problem. And this is one of the reasons why later we're going to introduce pivoting. But anyway, let's just not worry about whether or not it does or does not work. We'll just worry about that little detail later. Let's just see what happens if we push the symbols. So the first thing we notice is that when we were over here, what we were really doing is we were thinking of the first row as being special. We were thinking of this region of the matrix as needing zeros introduced. And then somehow the rest of this matrix needed to be updated. Okay, so this seems to suggest that we should take our matrix A and partition it into quadrants. And for good measure, let's do the same thing for L and U. Fair enough. All we did was partition our matrix. Typically, the next thing you do after you've partitioned the matrix is you multiply out the partitioned matrices. So in this particular case, we take this and we do a partitioned matrix multiplication, which by now you should be very familiar with. It's exactly like doing a matrix multiply with numbers, except you do it with the symbols there. And you need to be careful that you don't commute unless you are absolutely sure that you can commute. So this here becomes epsilon 1, 1, what? This times that plus this times that, that's that. This times that plus this times that gives us just U1, 2 transpose. This times that plus this times that gives us L21 times epsilon 1, 1, but that's a scalar, so we can actually bring it up front. Scalar times a vector is the same as a vector times a scalar. And then we get this times that plus this times that, which gives us L21 times U12 transpose plus L22 times U22. Fair enough? Now, we know that two matrices are equal to each other if the elements in the matrices are equal to each other. Which means that if we partition the matrices, then we should set the same regions equal to each other. So from this we conclude that alpha 1, 1 must be equal to epsilon 1, 1. A12 transpose must be equal to U12 transpose. A21 must be equal to epsilon 1, 1 times U12 transpose.
L.
L21, thank you. And A22 must be equal to L21 times U12 transpose plus L22 times U22. Okay, I like displaying it this way because then you can see that all we're doing is we're reading off the equivalent quadrants, right? You may have noticed by now in my notes that I often like to use white space and placement to help tell the story. Here I'm trying to help tell the story. And bingo! The first step of the algorithm stares you right in the face, because how do we compute epsilon 1, 1? That's just alpha 1, 1, right? How do we compute U12? That's just A12 transpose. Now, by the time we get here now, we know what A21 is and we know what epsilon 1, 1 is. So therefore, how do we compute L21? That's just A21 divided by epsilon 1, 1, right? Which is just taking a vector and scaling it. You've seen that operation before. And then by the time we get here, we know what this is, we know what this is, we know what this is. We would like to compute these. Notice that we can rewrite this as A22 minus L21 U12 transpose is equal to L22 U22. So notice what we could do. Notice that all we need to do is subtract. What kind of beast is this? That's a matrix. We're subtracting off. It's a rank 1 update, right? It's subtracting off a outer product from the matrix. Rank 1 update. So we do a rank 1 update to A22. And once we've done that, all we need to do is compute the LU factorization of the result. Okay? Now, it would be convenient to go ahead and just overwrite matrix A with the result. So in that case, all we do is we say like that. Notice that this, of course, is a no-op and this is a no-op, right? Nothing needs to be done. Here you just take A21 divided by what's now in alpha 1, 1. And then you would like to take A22, update it with A22 minus L21 times U12 transpose, which is just A22 minus A21 times A12 transpose. And obviously what you do is you just continue with this matrix, you partition off another first element, and you just do another step and you keep doing that recursively. Okay? And bingo, we've given ourselves an algorithm for computing the LU factorization. Under what circumstance does this algorithm break down?
Dividing by epsilon.
If you ever divide by 0, right? Actually, if you divide by something small, we're going to see that's also a bad idea. But, you know, strictly speaking, in exact arithmetic, if you ever divide by 0, you're a host. You with me? Okay. What do I need to say next? Well, what I need to say next essentially is to just give you what the algorithm looks like. And let's see if I can call that up on my computer here. I'll be writing my notes, so it should be in here somewhere. All right. Now, unfortunately, I went and I put two different interpretations of the same algorithm in the same. Why is this? Is that frozen? No, there it is. Okay, here we go. That's hard to see, right? Well, the skeleton of what's going on here. Oh wait, that has pivoting in it. Never mind. Let's go back. Ah, much better.
The resolution is.
It's pretty bad, huh? Is that getting better?
Kind of. See part of it.
Yeah, my resolution is messed up, isn't it? I don't know how that happened. How do I fix that? Let's go to preferences.
Kind of unplug and plug back in the projector.
Yeah, that might be the simplest. Okay, let's try that. Magically it fixed it. Good. Anyway, ignore what's on the bottom here, because I'm going to give a different interpretation of the same algorithm. And notice that here we're actually computing a matrix A, and we're L, and we're overwriting matrix A with U instead of overwriting. But obviously we can also just overwrite A with L below the diagonal, because we're introducing all of those zeros there, and we might as well put something there. And you might say, but wait a minute, if we store L and U both over A, then we are storing two diagonals, one for L and one for U. But notice that we know that L has 1s on the diagonal, and therefore we don't actually have to store those. So everything's cool. But here's the algorithm, okay? And you can ask yourself the question, does this actually work? Well, I went ahead and implemented this, but obviously if I went ahead and implemented this and then demonstrated, I'm cheating, right? So I should go and erase all of this. I hope I'm not sorry when I do that. All we do is go to the Spark webpage. We say we want to create an LU factorization. And I'll go ahead, I'm going to call this variant number 5 because there are actually 5 different algorithms for LU factorization. And it happens to be that we usually call this the 5th one. So there we are. And then we just take this. You've done this for QR factorization. We plug it in here. And all we were saying was, let's see, we said leave alpha 1, 1 alone, leave A1, 2 alone, take A2, 1 and divide it by alpha 1, 1. So here we'll say take A2, 1 and divide it by alpha 1, 1. And then take A2, 2 and subtract off a rank 1 update. So that's A2, 1 times A1, 2 transpose. And in theory, we now have an algorithm for computing the LU factorization. Okay? Should we see if we get the right answer? We can take A, we can create a random matrix that's 5 by 5, and we can then say let LU be, I called this LU unblocked variant 5 of A, and then we can extract L by saying take the lower triangular part of A, or the strictly lower triangular part, and add an identity to the diagonal. Oh! Okay, hold on. I should say L is equal to tri L of LU minus 1, right? Is that right? And then U should be the upper triangular part of the matrix LU. And then let's see if A minus L times U is approximately the 0 matrix, and it's approximately the 0 matrix. Okay? Now let's spend a little bit of time relating LU factorization to Gaussian elimination. Okay? What did we really do here? Notice that we computed the multiplier that told us what multiple of the first row we should subtract off of the second row. And then we did that, and then we took the multiplier that told us what multiple of the first row should be subtracted off the second row. But notice, sorry? This should be minus 1. Should that be minus 1? Well, no, because I said subtracted off. Okay, so it's this times that that's subtracted off of that, right?
But in the L matrix, I mean
in the L matrix, is there mistakes?
Yeah, in the L matrix.
Here? Oh.
I think that should be minus.
Nope. It should be 1. We'll relate those two together in a minute. Okay? So the multiplier will relate. It'll become clear in a minute. Okay? Be patient. So notice that we could have taken these two numbers and simply computed by taking these numbers and dividing it by the number on the diagonal. Here we simply took those numbers and divided them by the number on the diagonal. Okay? Then we said, oh, we need to do this times that subtracted off of that, this times that subtracted off of that, this times that subtracted off of that, this times that subtracted off of that. But if you think about that, that's doing this outer product and subtracting it off of these entries right here, which is exactly this. And then in LU factorization you say, and then continue with the sub-problem. And if you look at the algorithm here, you say, and continue with the sub-problem. So Gaussian elimination is simply LU factorization. Okay, now so by the time you've been in the field for like 30 years like I have, you have at least 10 different ways that you can explain every topic that comes along. Okay, this happens to be my favorite way of explaining the LU factorization. But a very useful way of explaining the LU factorization, and a more classical way, is to use something called Gauss transforms. And one of the nice things about using Gauss transforms is that it may look somewhat familiar because it'll look very similar to Householder transforms, which we used to take a matrix and compute its QR factorization. So let's have a look and see how that works. So we're going to cover the same topic, but we're going to take a slightly different view of the problem. Okay? Okay. So now, the fundamental problem I have, I guess I should leave this up. I may just get rid of the screen. I need some space. Okay. That way we can leave most of this out. Okay. I'm going to give you the fast version. Okay? Notice that inherently, as part of the computation, should I give a fast version? Yeah, why not? That's a dangerous thing. Notice that as part of the computation, what happens? You get to a point where this has been overwritten with an upper triangular matrix. All of these entries have already been zeroed out. Okay. And in the current step, what you do, all of these have already been updated because they were part of previous rows that we encountered as part of Gaussian elimination or LU factorization or whatever you want to call it. And at the current step, we're working with this updated matrix down here. Okay? And what essentially we just said was, when you then get to this point, you take this, you divide it into all of these entries right here, and then you take the result of that, multiply it by that, and subtract it off of that. Okay. And then you move the thick lines forward, and this is something that you implemented when you did QR factorization. And lo and behold, most density algebra algorithms can be formulated in this way. Okay? Now, it's out of curiosity, how many of you have heard of Gauss transforms?
Not many to go.
Two, a few. I never mentioned it in my class. Maybe not. I don't think so. Okay, I certainly mentioned it in the MOOC. But a Gauss transform, remember that let's not get ahead of ourselves. Let's look at a very special matrix. Minus sign here. Okay? If you multiply this times that, that's just partition matrix multiplication. Okay? First of all, this times that plus this times that plus this times that
shows that the first rows are left alone. Okay? This times that plus this times that shows that the zeros here are preserved. Okay? Let's see. This times that plus this times that plus this times that shows that this is left alone. This times that plus this times that plus this times that shows that this is left alone. And finally, you get that this times that plus this times that, this times that plus this times that plus this times that becomes this right here, which shows that this here becomes minus L21 times alpha 11 plus A21. Can you see that? No? Minus L21 alpha 11 plus A21. Better? And if you do this times that plus this times that plus this times that, you get minus L21 times A12 transpose plus A22 sitting right here. Okay? Now, if the objective is to set this to 0, how would you need to choose your L21? Well, if you choose your L21 to be equal to A21 times, divided by alpha 11, then this cancels each other, right? And what that means is, and then this here looks awfully familiar, doesn't it? That's exactly the update that we saw in the LU factorization that we saw before. Okay? And notice that again you can say, well, computing these right here is just computing the multipliers. The minus comes from the fact that you want to subtract off. And this simply then says, take multiples of this row and subtract them off of the rest of the rows, which is what verbally we describe when we talk about Gaussian elimination. Is it now starting to become clear where the minus sign came from? I don't know why that just came on. So we will blank it out again. And what do you notice? If we call this the kth Gauss transform, what you notice is that you start with a matrix A and you multiply a whole bunch of Gauss transforms from the left. Okay? Leaving you with an upper triangular matrix. Now, Gauss transforms are magic because their inverse is really easy to compute. Let's talk about that. Verbally, what does this particular matrix do? It takes multiples of one row and subtracts them off of other rows. The inverse of a matrix undoes what a matrix does. So if we just think through, what should the inverse of this matrix do? The inverse of this matrix should take multiples of that same row and add them to the other rows, right? The same multiples. How do we express that? That's the matrix that looks like this. And indeed, if you multiply these two matrices together, you get the identity matrix. Okay, now, why is that important? That's important because we give ourselves a little bit of room here. We can take L0, L1, all the way through Ln minus 1 and invert all of those. Whoops, we should do that in the right order though, right? But then we better do it in the same order on this side. Okay. And what we get is that this is just A, right? Now, what happens to a lower triangular matrix when you invert it? What's the shape of the inverse of a lower triangular matrix? It's a lower triangular matrix, right? If you multiply lower triangular matrices together, what do you get? A lower triangular matrix. So this here is a lower triangular matrix. Now here is the tricky part. This should be the exact same L that we got from the other LU factorization algorithm, right? Now in the other LU factorization algorithm, to compute L, in the first step what we said was just take these multipliers and place them right below the diagonal. And in the second step then we would have done the same and we would have placed the next L21. So this would have been more from the first step, from the second step, and so forth, right? So what that means is that multiplying the inverses of all of these Gauss transforms together is the same as simply placing the entries right there. Okay? Which certainly seems like magic. But if you look at one step of this, if you look at L0 inverse, if you look at the matrix that looks like this, and you multiply that times the matrix that looks like this, it's not that hard to see that the first column here becomes the first column of the result. How can you argue that? Well, a matrix times the first unit basis vector picks out the first column. Okay? And then it's not that hard to see that you do this times that plus this times that for the rest of the matrix, and that means you just take this and plop it right in there. And if you then just keep doing that with more and more matrices, you notice that indeed you're just plopping those multipliers in the place that the other way of deriving the LU factorization told you they should. Everything is magic here. Okay? Everything just falls in place. Okay? Which is actually classically how the fact that an LU factorization exists is typically justified in a linear algebra course. So in this undergraduate course for which you have notes, I go through this in much more detail and much more step by step, but I think you now have an idea of what's going on. Okay? And it turns out it's useful to have multiple ways of looking at the same problem, because when we now introduce pivoting, this is going to be important. All right? Any questions about this? It's actually in the notes, but it may be a little cryptic in the notes. So if the notes that I'm writing for the class now are a little bit too cryptic, back off, go back to the undergraduate notes to which I refer. Okay. Now, where should we go next? When did Gaussian elimination break down?
then things go horribly wrong.
Yeah, zeros.
If ever you encountered a zero on the diagonal when you had to divide by that number, you were hosed, right? What were you taught to do to fix that? Just
Switch rows.
You just switched rows and put a non-zero there, right? And that was Gaussian elimination with swapping of equations or swapping of rows or pivoting or whatever it was called. Okay? And then you could keep going as long as you never encountered a zero on the diagonal. Okay? Good. How can we introduce row swapping into the picture? Well, you may have noticed that I like matrices. They should have a, you know, these ads that they have for central markets. Do you like food? That ad. Do you like matrices? We should do that for our next offering of our massive open online course. That'd be a great ad. Anyway, we should talk to Central Market and see if they would make an ad for us like that. That'd be funny. Okay, I'm getting off topic. So, what kind of matrix can I use to swap rows? So, ever hear of something called a permutation matrix? Okay, so, let's say we'd had a zero sitting here. What we would have had to do is swap rows, which of course would have been the same as saying we would need to do something with all of this. And if you look at a matrix that looks like this, I want to keep this up. This is important. This can go. Okay, let's do our usual trick of having a matrix of x's. What happens if we multiply this by a matrix that looks like this? I like to partition by rows then. And notice you do this times that plus this times that plus this times that to create the first row. So notice that that moves the second row into the first row. And then this times that plus this times that plus this times that moves the second row, moves the first row into the second row, and then it leaves the last row alone, right? So similarly, what you notice is that when you encounter a zero, you could introduce a permutation matrix to permute the right rows somewhere else, right? And this is where the Gauss transform formulation of the of LU factorization sort of makes it a little bit clearer what really is going on. Okay? What really happens is that when you get to this point, you look at these entries, you decide which entry you should pivot to the top. That then introduces a pivot matrix. And then once you've pivoted, then you compute your multipliers so that you zero out these entries right here. And what that really means is that you start with your matrix A. You figure out with which row the first row should be permuted. After that, you figure out a Gauss transform that then annihilates. You then move forward.
you figure out another pivot matrix, except that that pivot matrix tells you with which the second row must be swapped to move on. You compute another Gauss transform, and you keep doing that. Actually, I think in the last step you can convince yourself you never will have to pivot because you're down to only one element, right? Let's leave it in there anyway. And the result of that is an upper triangular matrix U. Okay? And then the next thing that you can observe, which gets a little tricky and involves a lot of mathematics, so I'm not sure if I want to do this. I have a very clean description of this in the undergraduate notes, and I have a very clean description, well, clean but cryptic description of this in the notes I'm writing for this class. But it turns out that once you have computed all of these permutation matrices, you can actually rearrange all of these so that you can think of it as doing all of your permutations up front and then applying slightly changed Gauss transforms. Resulting in your upper triangular matrix U. Okay? And then you can say, oh, but that means that, what happens if you take a whole bunch of permutation matrices and you permute them together? Sorry, you multiply them together. You might as well think of it as just jumbling up all of the rows in some fashion, right? So all of these equal one big permutation matrix. And what it means is that we can write actually the result as this right here. Where these are slightly garbled Gauss transforms, which you can then multiply together to get a new unit lower triangular matrix. Okay? So, this is the way to think about it. You can think of doing Gaussian elimination, and you can think of, at every step of Gaussian elimination, making a decision of whether or not to swap two rows. Okay? And then along the way, eventually you get an upper triangular matrix, right? Or you could say, no, if I had been really clever, I would have simply started by arranging my equations in such a way that that zero was never encountered. And then I could have just done Gaussian elimination and never worried about swapping. The catch, of course, is that it's not until you start doing Gaussian elimination that you figure out which rows need to be swapped. But in mathematics, there is such a thing as hindsight. Okay? So mathematically, you can say, I should have been clever, I should have rearranged things. That's essentially what this is saying. You can take your linear system, permute it up front, and do LU factorization, or you can intermix the permuting of the rows as you go along. Either way, you end up with the same U. You do end up with a slightly changed, no, you end up with the same L along the way as well. Get my drift? I justify all of this mathematically in the notes, but every once in a while I sort of go, because I do it so carefully in the notes, maybe I won't do it in class. So I'm going to make you read it, okay? And if the notes, as I've written them, don't clarify it, go back to the undergraduate notes where I painstakingly go through it in much more detail. Okay? Good. Now, how do I bring all of this together? Okay. The purpose of the game is to solve linear systems. Do I have B or Y here? I erased it, so I can make it Y, because I think I use Y in my notes. What we have just done is said, look, you can do Gaussian elimination with pivoting. You can do LU factorization with pivoting to compute some way of expressing how the rows need to be swapped. Notice that that doesn't need to be a matrix, right? You just need to know the order in which the rows should be placed. So that's just an integer factor that tells you in what order they need to be. When you do LU factorization, where you do row swaps, this is what you get. If you then want to solve this, you can start with AX equals Y. Now notice that once you've actually done this, you do know what all of the permutations were. And you can apply those to the right-hand side. When you did Gaussian elimination, because the right-hand side was already appended, every time you swapped, you were also swapping the right-hand side, so that was happening implicitly. Or explicitly, actually, right? Implicitly, explicitly, whatever. One or the other. Depends on how you want to think about it, right? Okay? So you can simply say, take your vector y and permute it as necessary to mimic exactly what would have happened had it been appended and you were doing Gaussian elimination. At that point, this here now is this matrix L times U. Then you can say, make this a temporary vector z, solve LZ is equal to y hat, solve u x equals z, and you're done. Okay? Simple enough. If somebody hands you a new right-hand side, you can do it again. Notice that we don't compute the inverse of the matrix. I don't think we're going to talk about computing the inverse of the matrix. It's just a bad idea to compute inverses of matrices. Okay? And this is how it's done in practice. Now, mathematically, it is the case that if one never encounters an exact zero, then everything is cool, and mathematically you should be able to compute an LU factorization, right? Which is even more wonderful in the presence of round-off error, because if you start with a random matrix and you have round-off error, the chances that along the way you create an exact zero, slim to nothing. Right? Of course, you can always start with the matrix 0, 1, 1, 0, and it will fail immediately. But the fact is, and you could even then say, I know that a little bit of round-off is going to happen, so I'll just change this to the machine epsilon. That's practically 0. I'll change it to a small number, yes.
Well, bad things happen though once you divide by that.
I'm getting there, okay? So, the problem is that if you ever encounter a number that's very, very small, then you could also argue the other way around and say, if it's very small relative to all of the other entries, then maybe it is just noise, and maybe it really is a 0. And then really what happens is that all hell breaks loose, right? We should have pivoted. Now, what I'm going to do is in the next lecture we're going to look carefully at the backward error analysis of LU factorization. What I'm going to do is going to tell you what that result is, and then reason about that result to try to push us into understanding how we should be choosing our pivots as we go along, when we should be swapping rows, even if we don't encounter an exact zero. Okay? That's the strategy. Okay, so what is that result? Now, I've been known to sometimes write things down that are slightly wrong, so let me try to get this one right. Here it is. You probably want to keep this up. You probably want to keep everything up. Oh, we can get rid of this. So here is the result. You want to compute A is equal to L times U. Now, the fact is, okay, we're going to do this without pivoting, okay? The fact is that instead we compute an approximate solution, right? These are the computed L and U that come out of our algorithm. Round off or error happened. You're not getting the exact result. If this matrix is backward stable, what is it that we would like to be able to show? We'd like to be able to show that there is a small change to A that you can make, such that the computed L and U are the exact LU factorization of a slightly changed matrix. Correct? That's, and we would have to go through the kind of mechanism that we went through last time for dot product information vector multiply to come up with this. Okay? Okay. We would then like to be able to say that the change in A is actually small. This would be nice. Remember, this was n times the machine epsilon, or the unit round off, times 1 minus. I had a plus here last time, which confused some people because it's wrong. It should be 1 minus this, okay? That was our gamma n. So if we ignore this, this is roughly the size of the matrix times the round off error on, times the elements of matrix A in absolute value, tell you how to balance each individual entry in the change in matrix A that you would have to take. That would be fantastic, right? That would be a result that's as good as the inner product result that we have, essentially. But life is not that beautiful. There is a plus L check, U check that comes in. Okay, but remember, this is just all of the entries of the computed L in absolute value, which is of course the lower triangular matrix, times an upper triangular matrix where you took all of the computed values and you took the absolute value from those. Okay? Now, let's reason through what might happen to these entries here. Okay? We're doing Gaussian elimination. We encounter a 0. We divide by 0 to create the entries in L. Okay? The entries below the diagonal in L. What will be the magnitude of those entries? Infinity. Not a good thing, right? Which means that you end up with some pretty humongous entries in L and your hopes, right? If this bound can actually be attained. Of course, it could be horrendously pessimistic. Okay? And you can say, well, okay, never mind. We'll just be sneaky. We'll just put a small entry here, and then it's not 0, and then at least we don't get infinity, right? Well, not quite, because then these entries still might be humongous, right? You might get completely, well, you might get an LU factorization of a drastically changed matrix, which is probably not what you were after. Okay? Now, you could then say, okay, we don't do that. We'll just arbitrarily swap some row to the top. And now the question becomes, what is the smartest row to swap to the top? Okay? It's the one with the largest in absolute value. Why is that? Because then if you divide the other entries by it, you guarantee that the resulting multipliers are less than or equal to 1 in magnitude. Okay? Which if that's what you always do, what you just guaranteed is that your matrix L has entries below and on and below the diagonal that are less than or equal to 1 in magnitude, and that's pretty much the best you can hope for. Okay, so that's good. There's a secondary effect. If we ended up with a very large multiplier because we divided by a very small number, what you would end up doing is take a very large multiple of the current row and add it to the other rows, right? And what that would do is it would create very large entries in your matrix U. Okay, so having a very large multiplier has the problem that it creates large entries in L, but it along the way also amplifies the entries in U. That's known as element growth. Okay, so you get a double whammy. Multiply them together, especially when you take the absolute value of these things, you're hosed. Okay? You end up potentially with having introduced a humongous error in the matrix, well, the equivalent matrix for which you did compute the element factorization. So, the moral of the story is, every time you get to this stage, what you do is you look at all of these entries, you find the entry with largest absolute value. You swap that row to the top. You do a step of LU factorization. You apply a Gauss transform, however you want to think about it. You move on. Okay? And that's known as LU factorization with partial pivoting. Factorization with partial pivoting. Okay. Now the fact that there's this name partial pivoting means there must be something known as complete pivoting as well. Complete pivoting turns out to be completely useless. So I mention it in the notes, I'll just let you read up on it. But it's something that you need to be aware of. Essentially, in complete pivoting, what happens is that instead of looking for the largest value in absolute value here, you look for the largest value in absolute value in the entire matrix, and you swap both rows and columns. Okay? Which, of course, then means that you may end up with an even larger entry here, which may mean that you end up with even smaller entries in L and U, and there's some benefit to that. Okay, and that's LU factorization with partial pivoting, and that's how it's done in practice. And if you talk to most people, when you talk about LU factorization with partial pivoting, and you ask those people, is it numerically stable? They will say, yes, it's numerically stable. And unfortunately, strictly speaking, they're wrong. So there are matrices. So notice that because we said we can always think of permuting the matrix up front, This result here applies to LU with partial pivoting because you can always do the error analysis of the pre-pivoted matrix. And mathematically, even though practically you don't know this up front, mathematically you do know it up front, and therefore you can argue that this is just the result for the permuted matrix, and therefore this is the result for LU with partial pivoting. Okay? The problem, so the fact is, if you can construct a matrix A such that L and U have very large element growth anyway, then even partial pivoting can't help you because that matrix wouldn't even need any pivoting. Well, if you can do that for a matrix where you can show that every step you don't even need pivoting, then you know that LU factorization with partial pivoting is itself actually not numerically stable. After all, you construct a matrix that doesn't require pivoting, but it sees very large element growth. And indeed, you can actually come up with a matrix that shows exponential element growth, where the entries in U grow exponentially with the size of the matrix N. Yikes, not good. Okay? However, LU with partial pivoting has now been used for 40 years in practice, and people have never really ever run into this problem, and therefore people tend to not really worry about it. Okay? In the notes, I give a matrix for which you see exponential element growth. For those of you who are in the CSIM program, that question has been known to show up on the exam. Okay? Construct a matrix for which you observe maximal element growth. So you guys in particular should pay attention.